Lesson 1. Atomic Structure and Periodicity. Welcome to your first lesson on MATSEC IM Chemistry Fundamentals. Let us start by looking at the atom. According to the Bohr model, an atom's nucleus contains protons and neutrons, which are together known as nucleons, while electrons occupy shells outside the nucleus. Atoms of the same element always have the same number of protons, but they can have different numbers of neutrons. These are called isotopes. Because they have different neutron numbers, they have different mass numbers. To find the number of neutrons, simply subtract the proton number from the nucleon number. When we calculate the relative atomic mass of an element, like bromine, we take an abundance-weighted average of these isotopic masses. Moving on to electrons, we fill orbitals using the Aufbau principle. For example, phosphorus has 15 electrons, giving it an electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p3. Calcium ends in 4s2 and is in group 2, making it an S-block alkaline earth metal. Finally, let us discuss first ionization energy. This is the enthalpy change when 1 mole of gaseous atoms loses 1 mole of electrons to form unipositive gaseous ions. Across period 3 from sodium to argon, the first ionization energy generally increases because the nuclear charge increases while shielding remains similar, holding electrons more tightly. However, there are small irregularities. For instance, the first ionization energy of aluminum is unexpectedly lower than that of magnesium. This happens because aluminum's outermost electron is in a 3p orbital, which is higher in energy and more easily removed than the 3s electron in magnesium. Lesson 2. Chemical Bonding and Structure. Let us explore chemical bonding and molecular structure. Ionic bonding is the strong electrostatic attraction between oppositely charged ions formed by electron transfer. Solid sodium chloride has a high melting point because these strong electrostatic forces hold the cations and anions together in a giant ionic lattice. But bonds are not always formed by electron transfer. In the ammonium ion, nitrogen donates a lone pair into an empty orbital on a hydrogen ion. This is known as a dative or coordinate covalent bond. We can predict molecular shapes using VSEPR theory. Take boron trifluoride. It has 3 bonding pairs and no lone pairs, so the electron pairs arrange themselves at 120 degrees to form a trigonal planar shape. Ammonia also has bonding pairs, but it includes 1 lone pair. This lone pair repulsion compresses the tetrahedral angle down to about 107 degrees. Shape also influences polarity. Water is a bent molecule with polar bonds that do not cancel out, giving it a permanent dipole moment. In contrast, linear molecules or highly symmetrical ones like carbon dioxide and carbon tetrachloride are completely nonpolar overall. Intermolecular forces drastically alter physical properties. For example, hydrogen fluoride has a much higher boiling point than hydrogen chloride because of strong hydrogen bonding. Hydrogen bonding is also the reason ice is less dense than liquid water. It creates an open lattice structure that holds water molecules farther apart. Finally, let us compare giant structures. Diamond is very hard because each carbon atom forms 4 covalent bonds in a 3D giant structure. Graphite is soft because its hexagonal layers are held by weak forces, allowing them to slide. Meanwhile, metals are excellent electrical conductors because their delocalized valence electrons can move freely under an applied potential. Lesson 3. Moles, stoichiometry, and gases. In this lesson, we will tackle the mole concept, stoichiometry, and the behavior of gases. 1 mole of any substance contains Avogadro's constant, which is 6.02 times 10 to the power of 23 particles. By finding a compound's relative molecular mass, which is the sum of the relative atomic masses of every atom in the formula, we can convert between mass and moles. For example, carbon dioxide has a relative molecular mass of 44.0. We can also use mass percentages to find a compound's empirical formula. If we know the empirical formula is CH2O and the relative molecular mass is 180, we find the molecular formula by dividing 180 by the empirical mass of 30, giving us a factor of 6, resulting in C6H12O6. When predicting reaction outcomes, we must identify the limiting reagent. If you mix 0.100 moles of magnesium with 0.080 moles of hydrochloric acid, the acid is the limiting reagent, because magnesium would require twice its amount in acid to fully react. If you perform a combustion reaction and collect 18.0 grams of carbon dioxide, when the theoretical mass is calculated as 22.0 grams, your percentage yield is roughly 82%. We can also measure gases. Avogadro's law states that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. This means gas volumes react in simple mole ratios. Finally, we use the ideal gas model, which assumes there are no intermolecular forces between gas particles. Using the ideal gas equation, where pressure times volume equals the number of moles times R times temperature, we can accurately calculate the pressure of a gas. Lesson 4. Enthalpy and Thermodynamics. For our final lesson, we will look at enthalpy and thermodynamics. Reactions often involve heat changes. An exothermic reaction is one in which heat is released to the surroundings, meaning the overall enthalpy of the system decreases, and the change in enthalpy is negative. Chemists use standard definitions to compare these changes. The standard enthalpy of formation is the enthalpy change that occurs when exactly 1 mole of a compound is formed from its constituent elements in their standard states. To estimate enthalpy changes for reactions in the gas phase, we can use bond enthalpies. Keep in mind that mean bond enthalpy terms are only approximate. This is because they are average values calculated over similar bonds in many different molecules. To estimate the enthalpy change of a reaction, you subtract the bonds made from the bonds broken. If the bonds broken total 678 and the bonds made total 862, the estimated enthalpy change is 678 minus 862, giving negative 184 kilojoules per mole. Another crucial principle for calculating enthalpy is Hess's law. Hess's law states that the overall enthalpy change of a chemical reaction is independent of the route taken and depends only on the initial and final states. Finally, when studying phase changes, remember that saturated vapor pressure is the pressure of a vapor that is in equilibrium with its liquid or solid phase at a given temperature. Thanks for watching. For free practice questions, study guides, and flashcards, visit exampreprise.com. Good luck on your exam!